My name is Colin Tranter. I'm a graduate student in engineering at Louisiana Tech University. I'm making this presentation as part of MSc 505. Today I'm going to talk about nanoscale surface modification for microfluidic applications. It's something my research at Tech pertains to, and I'll give a little bit of an intro to the subject. Microfluidics is a field that deals with small volumes in laminar flow. Numerous processes have been performed on the microscale, including DNA amplification, PCR, and DNA analysis, protein analysis, cell manipulation, and separation. Devices capable of these processes are usually low power and open the doors for potentially portable systems. Well-known portable devices include the tricorder as seen on Star Trek, or the metachlorian counter used in Star Wars Episode 1. Just kidding, but really devices like these may not be too far off. Actual devices are fabricated from polymers such as PDMS or SU8, glass, and silicon. Microfluidic devices have high surface area to volume ratio, leading to increased sample and substrate interaction. This can be made beneficial, but is often a very large obstacle to overcome. Nanoscale surface modification comes into play in microfluidics for various reasons. Surfaces are often modified in order to pacify them, preventing parts of the fluid or the reagents from interacting with the surface. Surfaces are also modified for functionalization, changing the surface chemistry of the device, often to trap some analyte from the sample. Surfaces can also be modified to promote bonding. Microfluidic devices often consist of microchannels, and encasing these between two wafers is an important fabrication step. Changing the surface chemistry of a device, making it hydrophobic or hydrophilic, changes the wetting properties. Patterning these wetting properties has been explored recently for greater fluidic control. Surfaces are modified in a variety of ways. Salinization is when silicon-containing molecules are covalently bound to the surface, adding an almost endless variety of chemical groups. Competitive binding is when a reagent is added to the sample to prevent the interaction of a certain analyte with the surroundings. The added reagent can either interact with the analyte, preventing it from binding, or interact with the surface, preventing the analyte from binding. Surface roughness modification can lead to changed wetting properties, often making a surface very hydrophobic. This can be done with laser ablation, but is often paired with some other type of modification, such as salinization. Initiated chemical vapor deposition, ICVD, is a process similar to regular CVD, but a highly reactive intermediate is added to the reaction to get it to carry out at a much lower temperature. This is important in some devices where polymers are used as a substrate or some other temperature-sensitive surface has been added. A variety of analysis techniques can be used depending on the type of coating. Optical and fluorescent microscopy are used in the image to the right. A and B are images of an untreated channel, where C and D are images of a silane-treated channel. This silane is a fluorescent molecule and can be seen in D, a fluorescent microscopic image, where it can't be seen in B, a fluorescent image of the untreated channel. Scanning electron microscopy is especially useful to look at surface roughness changes induced on a channel, or to look at the structure of more complicated surface treatments. Fourier transform infrared spectroscopy is the most commonly used tool to look at the chemical composition of a modified surface. Water contact angle measurement and flow measurements, somewhat atypical when analyzing nanotechnology, are indispensable when looking at the effects of nanotechnology on microfluidics. These analysis methods are great for looking at the modifications or quantifying some part of the coating, but device performance is the real test to determine the success of the coating. Quantifying the process efficiency, depending on what the device was designed for example, PCR efficiency, how the coating facilitates PCR, the replication of DNA, or the change in signal-to-noise ratio when looking at some fluorescent signal out of a device. It can be useful to compare different types of treatments on different substrates to determine which type of coating is best suited for a certain process. For example, silicon, SU8, and glass devices, either untreated, silane-treated, or protein-treated, were all compared for PCR efficiency. It was found that the protein coating worked best for PCR efficiency, but if such a device is used for multiple purposes, such as fluorescent analysis of DNA, one coating may not be able to be best suited for all situations. The success of surface treatments is instrumental to the success of microfluidic devices. Ease of fabrication of the coatings and reliability of performance brought on by these coatings can lead to successful devices and allow widespread use of microfluidic technology. Integrated devices are currently in use and on the market for high-throughput research, medical diagnostics, and portable analysis. In conclusion, microfluidics deals with small volumes and has been applied to numerous processes. Devices are fabricated on polymer, glass, and silicon substrates. Nanoscale coatings are used for passivation, functionalization, bonding, and advanced wetting. Fabrication techniques include siliconization, competitive binding, surface roughness modification, and initiated chemical vapor deposition. Analysis techniques include various forms of microscopy, Fourier transform infrared spectroscopy, water contact angle, and flow measurements. Device performance is the real test to determine the success of a nanoscale coating in microfluidics. So I guess the question is, are nanotechnology enabled devices like this bringing us one step closer to devices like this? Thank you.